Hey guys, how's it going? So today we're going to be looking at proof by contradiction with the help of a couple of examples. So basically what proof by contradiction is that we're aiming to get our proof by contradicting the initial hypothesis. So what you have is you have the question, which is the proof, which is the actual question. Then you have the proof by contradiction, which is the opposite of that initial question. So you base your entire investigation on that proof by contradiction. And once you arrive at the final conclusion, you conclude that the proof by contradiction is false, thus rendering your original hypothesis true after all. And it's actually quite a critical process because you start off by assuming that your hypothesis is false, as opposed to direct proofs, which assume that the hypothesis is true. So let's go into an example. So we have example 1, proving that there is an infinite number of natural numbers. Now we know that isn't really true because there is an infinite number of natural numbers, but then for the sake of argument, let's assume that there is a finite number of natural numbers. And let's have x as this so-called largest natural number. But what happens when you have a number that's larger than x? So what about x plus 1? And for the sake of argument, let's have that as x1. So x plus 1 gets you another number that's larger than x by 1. And that number, let's call that x2, which is x1 plus 1. So x2 is larger than x1. And that renders your original argument that there is a finite number of natural numbers, that argument is now false. And if you go to Sherlock Holmes, what he said was, that's quite interesting, because what he said was, when you have eliminated the impossible, whatever remains, however improbable, must be the truth. So we have eliminated this statement, and what remains is your original statement, that there is an infinite number of natural numbers. And that is true. And we have arrived at that conclusion through algebraic manipulation and using proof by contradiction. So let's go on to another example, just to really drive this concept home. So we had to prove that the number of two even numbers is also even. So logically, that fairly makes sense. So you have 2 times 6, that's 12. 2 times 7, that's 14. Both are even numbers. You have 8 times 8, 64. 10 times 10, 100. 12 times 12, 144. And what's common with all of them? They're even numbers, and we know that for a fact. But what if that really isn't enough to convince ourselves? So that's where proof by contradiction once again comes in. So you have P, B, C. Let's assume that the opposite of this hypothesis. So prove that the product of two even numbers is actually odd. Let's take that for example. So, and thus we begin our proof. Let's have two variables, x and y. And they happen to be even numbers. So x is equal to 2p, y is equal to 2q. And p and q are both natural numbers. And that's fairly simple so far. So we have xy equivalent to 2pq. And so xy is equal to 2p times 2q. And using brackets gives you 2q. That's fairly simple so far. Sorry, excuse my handwriting. And you end up with multiplying those gets you 4pq, which is equivalent to xy. Simplifying this gets you here. That's 2pq. And what you use to multiplying this happens to be an even number. And it's interesting because that isn't an odd number. And if it was an odd number, that would be true. But in this case, it's an even number. Hence, that is false. And if you go back to Sherlock Holmes, funny illustration right there. But whatever is impossible, when you eliminate that, whatever is remaining is the truth. And so the product of two even numbers is also even. And we have proven that using proof by contradiction. And that's basically it.